All right, so in this video, we're going to be looking at how to solve a two-variable system of equations. We're going to solve it by row reducing, and then we're also going to solve it with inverses to see that we get the same solutions. So we're going to begin with row reducing, since that's sort of the standard way of going about this. And let's come up with some brackets. And we're going to have our 2 by 2, and we'll add the bar here just to make the spacing a little bit clearer in the system. And we'll put in our coefficients: 2, 1, 3, -1, and 15, and 5. All right, now, according to row reducing, we are going to need to introduce a 1 into this top coordinate. And there's a couple of different ways that we could go about this. We could just divide that first equation by 2 and just deal with the fractions. Another alternative is we could try to be a little bit clever about this. If I took row 3 and subtracted row 1 or row 2 and subtracted row 1, for instance, then I would get 3 minus 2 would be 1. And so I would actually get my 1 without having to introduce fractions. So that's what I'm going to do. Row 2 minus row 1, and then I'm going to put that back into row 1. Now your calculator will almost never do this, so just be aware that your calculator will proceed probably in a more just sort of straightforward fashion, and it'll just divide the top row by 2, and then it'll introduce fractions, and then it'll just work with the fractions. They're a little bit slower for people, and so I usually try to avoid them. All right, so row 2 minus row 1, 3 minus 2 is going to give me a 1. And then -1 minus 1 is going to give me a -2. And then 5 minus 15 is going to give me a -10. But I've got my 1. So now I'm going to get rid of the 3. So -3 row 1 plus row 2. And I'm going to put that back into row 2. Now, -3 times 1 is going to give me -3. Added to 3 is going to give me a 0. And then -3 times -2 is going to give me a 6. +6 added to -1 is going to give me a +5. -3 times -2 is +6. Added to -1 is going to give me a +5. -3 times -10 is going to give me a +30. Added to 5 is going to give me a 35. That is not quite typing correctly. There we go. 35. And then I got my 1, and everything below it is a 0. So now I can move on to my next pivot. I'm going to divide that by 5. So 1/5 row 2 goes to row 2. So this will become a 1, and 35 divided by 5 is going to give me a 7. And then if I want to solve this, I can back solve it, or I can do one more row operation. I can say 2R2 plus row 1 goes back to row 1. So 2 times 1 plus -2 is going to give me 0. And 2 times 7 is 14, plus -10 is going to give me 4. And so either way, I'm going to end up with 4, 7 as my solution. Great. That is the row reducing method. Well, what about inverses? Well, for the inverse for a 2x2 matrix, there is a nice formula. So suppose that I have A is equal to A, B, C, D. Then I know that A inverse is going to be 1 divided by AD minus BC. That's the determinant. And then inside my matrix, I am going to switch the positions of D and A, and then I'm going to flip the signs of B and C. So recall that essentially my system of equations is an equation of the form AX equals B. And if I multiply both sides by A inverse, then I end up with X is equal to, the solution to my system is equal to A inverse B. So if I can find the inverse of my original matrix, then I can just multiply by my original column of constants. Now, my original matrix A is just going to be this part of my matrix right here. So 2, 1, 3, -1. So let's actually just write that down. In this case, 2, 1, 3, -1. And so my inverse is going to be, okay, so AD is going to be -2 times, well, -2 minus 3 times 1 is 3. And then my matrix is going to, again, swap A and D. So -1 and 2, those are switched in position. And then the signs change on the other two. So -3 and -1. And so I have -1/5 times these guys. And if I distribute, I'm going to end up with +1/5 and +1/5 and 3/5, again positive, and -2/5 for my inverse. And so now my solution to my system X is going to be A inverse B. So that's going to be this guy. Times my vector. And if I scroll up to find my coefficients, they were originally 15 and 5. So 15 and 5. Again, remember you're using the ones from the original system, not from some intermediate process. And now we have to do matrix multiplication. So 1/5 times 15 plus 1/5 times 5. And then 3/5 times 15 minus 2/5 times 5. So 1/5 times 15, that's going to be 3. 1/5 times 5 is going to be 1. And down here, the 5 and the 15 are cancel. I'm going to get a 9, but then the 5 and the 5 cancel and I get a -2. And so I do, in fact, end up with the same answer I got before, which was 4 and 7. Now, this inverse process isn't too bad for the 2x2 because there is a nice formula for the inverses. But it is terrible when the matrices get bigger than this. Finding the inverses, honestly, you might as well just do the row reducing because you'll have to, the only way to do it by hand is to do the row reducing method by hand. And then you're going to end up doing more work than if you were just doing the row reducing anyway. If you have technology and you can get the inverse by technology, then this works fine for larger matrices. But, you know, again, from it's a step-by-step standpoint, you're just letting the calculator do all the work for you. So this does, both of these processes do give you the exact same answer. But how much work you're willing to do, what method you think is more straightforward, you know, that your mileage may vary.